Gateway cloning. SnapGene allows you to simulate standard and multi-site gateway cloning with unprecedented ease. Just specify the fragments to be stitched together, and the software will design suitable primers. As an example, I'll start with the simple cloning of a plant gene, cDNA, into a custom gateway vector. The gene is Arabidopsis HDT1. HDT1 will be cloned into the plant gateway vector p-earlygate103, which I downloaded from the SnapGene website. The vector contains a GFP gene, which will be fused to the C terminus of HDT1, so I'll need to avoid the stop codon of HDT1. The first step is to transfer HDT1 to a donor vector using BP cloning. I open the Actions menu and choose Gateway Cloning followed by BP Cloning. The dialog opens to the @B Insert tab, and HDT1 is already chosen as the source of the insert. I want to select the gene without the stop codon, so I switch to Sequence View, then click to select the start codon, then scroll down to the end of the gene, then shift-click to the final lysine codon. When I switch back to Map View, the entire coding sequence is selected. Now I switch to the Donor Vector tab. I click in the list to select pDonor221, which is a standard donor vector. Finally, I need to specify primers to amplify HDT1 with @B1 and @B2 sites so that it will recombine. For this purpose, I could enter primers manually into the @B Insert tab. Instead, I'll let SnapGene design suitable primers automatically. I switch to the Entry Clone tab and press the Choose @BPCR Primers button. I stay with the default settings and press Choose Primers. At this point, the green box says that I'm ready to clone. The overview at the bottom shows that the @B sites in the amplified gene will recombine with the @P sites in the donor vector to create @L sites. I could proceed with the cloning now, but to see the primers, I switch back to the @B Insert tab. The red regions in the primers are the @B1 and the @B2 sequences. I click in the product name box and edit the name to HDT1 entry clone. Now I press clone, and the entry clone has been created. If I switch to history view, I see the amplification and recombination steps. The next step is to transfer HDT1 from the entry clone into my destination vector. I choose Gateway Cloning followed by LR Cloning Insert Fragment. The entry clone is already chosen. I switch to the Destination Vector tab and choose p-earlygate103 from the Custom Destination Vector menu. That's all I need to do. I could proceed with the cloning now, but to preview the result, I switch to the Expression Clone tab. The overview at the bottom shows that the @L sites in the entry clone will recombine with the @R sites in the destination vector to create @B sites. I edit the name to HDT1 Expression Clone. When I press Clone, the final product is created. To see the fusion junction, I click to select the @B2 feature, then I switch to Sequence View. I see that HDT1 is fused to the GFP gene by an in-frame linker. Now it's time for a more complex example that shows off the full power of the gateway cloning interface. I'll close these files and open the files for a two-fragment gateway cloning. My present construct has GFP fused to a human protein called Sec16b with the Sec16b gene in the antisense direction. I'll fuse the snap tag shown here in purple to the N terminus of Sec16b in place of GFP. This time I'll do a two-fragment cloning, and I'll simulate the BP and LR cloning steps at the same time. I choose Gateway Cloning followed by BP plus LR Cloning Insert Two Fragments. This time there are two @B inserts. The first one will be the snap tag, so I click on this feature to select it. I know from previous work that the snap tag gene lacks a stop codon, so it can be fused to the N terminus of Sec16b. To specify the second @B insert, I click on the To button at the upper right. From the menu, I choose PMEGFP Sec16b.dna. Then I click on the Sec16b feature to select it. Now I switch to the Donor Vectors tab. For two-fragment multi-site gateway cloning, I'll follow the company guidelines and use pDonor221P1P5R for the first donor vector and pDonor221P5P2 for the second donor vector. I click on the Entry Clones tab. These clones will be generated later once the primers have been specified. Then I click on the Destination Vector tab. I choose pcDNA 3.1 and v5dest because I want to fuse an additional v5 tag upstream of the snap tag. I'm ready to design primers, so I switch to the Expression Clone tab and click Choose @BPCR primers. Notice that for each of the @B inserts, I have two options for the orientation of the @B sequences. @B insert 1 is the snap tag, which is encoded in the sense orientation, so I stay with the default option. @B insert 2 is Sec16b, which is encoded in the antisense orientation, so I click the second option. Now I press Choose Primers. The overview shows the recombination events, and the map shows that Sec16b has been fused to the snap tag as desired. When I press Clone, 3 sequences are generated. At the top of the pile is the expression clone. I switch to Sequence View and scroll down to see the junctions. The V5 tag is followed by a TEV protease site, which is in frame with the SNAP tag, which in turn is in frame with Sec16b. When I close this file, I see the second entry clone encoding Sec16b. When I close this file, I see the first entry clone encoding the snap tag. Such an entry clone could be used again if I chose to simulate multi-site gateway cloning starting at the LR cloning stage. As you have seen, gateway cloning is a versatile technique, and SnapGene is designed to guide you through any variation that meets your needs.